Thank you very much for attending this webinar on the next challenges in 6G for programmable and deterministic networks. We had a last minute change in the agenda because unfortunately Mark has a personal issue tonight, okay? So he had to leave for Valencia, his home town, in the early morning. So he couldn't join, okay? So unfortunately, we are going only to present and to have the views of deterministic 6G and design 6G on this important matter. Although I'm here, I am Antonio de Oliva, who is the coordinator of the Predict 6G, and I hope that by my questions we can explore also the challenges that we see in Predict 6G. So our first speaker is James Gross. You can see the screen, right? Because something changed here. Okay. James Gross from Deterministic 6G, that he's a professor in the School of Electrical Engineering and Computer Science at KTH. Okay. I know him from different events that we had and UCNC a couple of years ago when we held our first joint workshop of the two projects that right now in the Horizon Europe are leading the work on reliability in the network, basically in 6G. Okay. So he has a very strong background on different kinds of communications. He's chair of the transactions on wireless communications, and he has a strong background on network calculus and network simulation. The next speaker coming from the 6G will be Gergely Pongrad, that is a senior researcher and information technology expert at Ericsson Research in Budapest. And Gergely, I promise that at some point of time I will be able to say your name correctly. Sorry for that. And we have been working together in the.
You don't have a chance, Antonio, but that's not your fault.
Well, I will try. And he's very well versed in all the programmability stuff in switches P4, and he really has a deep background and understanding on what can be done with programmability in the network. So without waiting anymore, I will pass the floor to James so he can start the presentation. Thank you very much.
Excellent. Thank you, Antonio. First of all, hello, everyone. This is interesting news that we're only two speakers. Huh? That means we can go much more relaxed upon the time, I guess so. Let's see how it turns out. Let me share my screen with the material that I presented for you. Here we go. Can anyone confirm that you're seeing what I'm seeing?
Yes.
Does it look good? Yeah? Okay. Good. All right. So again, good morning, everyone. My name is James Gross. I'm the technical manager from deterministic 6G. And I'm very pleased to be invited to this seminar, to this webinar, to be correct, to speak a little bit now about essentially the outcome of deterministic 6G. We have been running, I think, as the other two projects now for a little bit more than 2 years. We're all, I think, within the next couple of months coming to the end of the project runtime. And so it's high noon, it's high time to look a little bit what actually came out and how the different projects are perhaps seeing the way forward. And in that sense, it's pity that the third speaker cannot make it. But let's see if we can derive anything valuable still from the two speakers that are here today. So I have here a couple of slides that I put together, mostly around the motivation, the background for deterministic 6G. This is just a little bit warming up. Then I would like to get to a couple of architecture insights that we think are central to dependable 6G networking. You will see during the presentation that we had quite some, let's say, quite some philosophical and also other issues with naming the project. We actually started not with deterministic 6G, but we started with Einstein 6G. Then we morphed to deterministic 6G just to figure out that perhaps determinism is also the wrong expression, but we'll come to that when I'm talking about here architecture. And then I would like to embark with you on 2 deep dives on 2 sections in deterministic 6G where we have made some progress. This relates mostly to latency prediction and then wireless friendly TSN scheduling. There are a couple more or many more areas actually where people have been doing very, very good work. So we had a very good harmony in the entire project, and everyone was trying hard to pull off good results. So this is right. These are not the only 2 deep dives that we could do, but these are the 2 that I'm selecting for today, and then I'll have some conclusions and also some comments on the way forward. And Antonio, how is this, or the team from Australo? How shall we deal with questions? Shall we take them? Do you want them to be taken at the end?
I think it would be better if we take them at the end of your presentation, because if not, it's going to be difficult.
Good. All right, then I'll just fire along. Good. All right. So then let's have a little bit look at where we were standing 3 years ago when we put together the proposal for deterministic 6G, and the starting point were so-called time-critical applications, and in particular, time-critical applications with that are processing in any type states in reality, and then also providing feedback on them. So we see, and I think we're seeing this already for 10 years, an increasing number of these time-critical applications. The original starting point here was, of course, the discussions we had 10 years ago in 5G around industrial automation. But since then, a healthy set of additional applications have been joining here the mix. And this in particular relates, the thing that gets bigger and bigger and bigger these days is, of course, then anything around extended reality. And in many of these real-time looped type of applications, we see relatively strict requirements on bounded latency and also high availability. And we have here a couple of use cases, as I said, so extended reality, of course, flexible production manufacturing is the second one that comes more from industrial automation. The third one that is, let's say, not so prevalent in literature, but that is very, very interesting and also falls into this class are occupational exoskeletons. And then also smart farming falls into this area. So these are all looped applications that in particular have as a common core the necessity to process a relatively large amount of data in real time somewhere on a near, or at least in terms of latency, near computational offloading point, which can be the edge, which could also be somewhere deeper into the infrastructure and then with the cloud. And it is foreseen, or some people think that as in 5G, we were, let's say, focusing more cyber physical systems, as we now see more and more a proliferation of these integrated reality processing application classes, these closed loop application classes, that this will become turn more into a cyber physical continuum. So think of that in terms of, for example, XR applications. If you start to run them at scale over a certain spatial domain, so over a city or over any other stretch of land, then there comes a point, right, where you start to really collect a lot of information, right, about this the spatial domain, right, and so right, you then enter conceptually, you could enter a situation where more or less anything, any area in your city or so is covered by such an application, right? Leading to the situation that you have a continuous representation of the real world, also in the cyber domain. And this is what then the cyber physical continuum relates. And those of you that ran over these keynotes and presentations and so on and so forth, you know, of course, that this vision of the cyber physical continuum is a main driver, in particular of Ericsson, towards 6G. Okay. Now, the challenge with this is that from a 5G perspective, while individual components had already been defined and then also standardized, think in terms of URLLC, think in terms of edge computing, the facilitation of such a cyber physical continuum at scale and in an efficient way, this is not achievable by 5G. And this led then to the rise of the project deterministic 6G, and to be honest, also other projects, of course, in this batch of SNS projects, or in general, these SNS projects that have been all staged around 6G. In our case, we had here the vision to work from a couple of novel use cases, and this was in particular exoskeletons, these occupational exoskeletons, where we had a corresponding partner. Then also over a couple of use cases in the industrial automation domain, and then look into different types of enablers that would allow, at the end, a new system architecture, would at least point to components of a new system architecture for such dependable 6G or dependable and time-critical reality processing applications. Okay, and in this mix of these different enablers, there's then we consider 6G wireless transmission design, characterizations, data-driven characterizations for 6G systems, time synchronization. But then, and this was a relatively big footprint of deterministic 6G, the integration, the more efficient integration of future 6G systems into deterministic communication standards. And this was in particular TSN and DetNet. And then we had also work packages or tasks where we looked into edge computing, situational awareness, and security security aspects, security by design, and so on and so forth. Deterministic 6G also focused a lot on validation frameworks, and there we also have a couple nice results that we will be spinning out, have been spinning out, and will still be spinning out over the next couple of weeks and months to the community. And you see here at the bottom the key partners in deterministic 6G. This was, of course, KTH, where I'm from. Ericsson was had a strong footprint in deterministic 6G, and then a couple others, BNR, SAL, UVO, and so on and so forth. You find, of course, all the information about this on our webpage, and I have a couple more pointers coming. All right, so we spent in the project at the beginning quite the time to discuss determinism, guarantees, and where these things were coming from, also with respect to the automation, with respect to the automation community. We settled then for naming to classify these time-critical applications in a way that they are requiring or demanding dependable communication services from the infrastructure, and perhaps then also from the compute backend. And dependable communication in our mind is characterized by being able to quantitatively ascertain the delivery or required service performance for the communication that is agreed. Now, this comes with a twist, and the twist is, in our mind, that these agreements are renegotiated from time to time. So where you have perhaps a fixed agreement in 5G, according to different industrial automation classes. In our mind, going forward towards 6G, we see the necessity for these dependable communication negotiations, so to say, between the applications and the infrastructure, to be happening more frequently, or at least to have the primitives in the system, that these agreements can be renegotiated. Okay, and then it is really also very important to stress this aspect of this quantitative guarantee. Different of these time-critical applications come with quite some different quantitative requirements, and also these quantitative requirements are in the stochastic domain. So you have requirements that are in the that we talk about, let's say, a certain percentage of packets to be delivered within a certain latency bound. So you need in the architecture means to monitor this, and then also to optimize your system and steer your system towards always guaranteeing or reaching these quantitative levels. And this is quite some obstacle, or this is quite challenging, but can be decomposed into several steps. And this is then one major outcome of the project when it comes to architecture. Of course, I'm simplifying here a lot in the interest of time. So we see the need for clarity on required and agreed service performance negotiations, in a sense. Then there must be in the infrastructure a certain ways to monitor this and to also predict the delivered service performance as it is conducted. There must be certain support for automated service assurance, and there must be also feedback mechanisms when it comes to the service delivery to the application domain. Just to visualize that, I have here a nice plot on the next slide. So you have here typical architecture outline with the different domains over which your mobile communication is spanning. On the left side are the devices. On the right side are more the edge or cloud compute backend points. And then you have here, first of all, the specification. This is step number one of the requirements from the applications towards the infrastructure. In two, you have end-to-end and overall intermediate steps. This monitoring and then also prediction business of the service as you're conducting it. Three is then mechanisms to automate, to assure an automated way towards the application that the agreed on service levels are actually achieved. And then four allows you this renegotiation between the application and the infrastructure in case, for example, that the infrastructure sees that over a future time horizon, maybe certain requirements cannot be met. Now, this was, so to say, then the chosen philosophical architectural way forward for deterministic 6G. And in particular, we were very interested in integrating this with end-to-end deterministic communication, and here in particular, with 802.1 time-sensitive networking, with the possibility also to configure such setups through application middleware like OPC UAFX. And there we also, in these domains, we had quite a lot of standardization contributions. Good. Now I would like to switch gears a little bit and get to the two different enablers that play a central role. And we are touching here in this figure, on the one hand side, the predictions, so on 2. And on the other hand side, we are touching what you could say as 3 and 4, essentially the service assurance, and then also the renegotiation capabilities. And this is relating to what we call wireless-friendly PSN scheduling. So when it comes to latency predictions, we had already at the beginning of the project some state-of-the-art which related to probabilistic data-driven predictions through mixture density networks. So think in terms of, in a very simplistic way, you're sitting in front of a 5G link, and you're asking yourself, you're kind of like, right, you're running certain packet stream over the 5G link. You're, for example, now interested in link layer latency from the UE to the infrastructure. You're seeing a sequence of these latency measurements. For every packet that you're transmitting, you get a new latency measurement, new latency sample. And you're wondering into the future, so well, how likely is it now, for example, that the particularly bad latency threshold is overstepped? And there we had already been, at the beginning of the project, we had been showing that if you use mixture density networks and you marry them with extreme value theory, that you can come with very, very few samples to very, very good latency predictors. In particular, when it comes to the tail, so the really bad and high latency values as they're evolving. Now fast forwarding 2 years, we looked then very extensively into time series forecasting. So we moved away from these rather, let's say, simplistic latency predictors and move more towards time series interpretation of the problem with temporal prediction structures. And all of you, of course, know them, and I highly suspect all of you are using these temporal prediction mechanisms these days on a daily basis, because this is the base to transformers, and transformers are the base to large language models, and all of us, I guess, are using them very extensively. So a question was for us, so do these time series forecasting, these temporal prediction architectures, so to which degree of performance improvement can we drive them? This comes then also with the necessity to manage the data dimensions. So you need a certain tokenization to leverage these large language models or these transformers. And this is something that we then studied. So in particular, we looked into a setup where you had a stream of packet delay values. And this is your packet delay context vector, xn, which has H, capital H, historical latency values. And then we were interested in a probabilistic forecast for the delay distributions over the next L future packets that were coming. Okay, and this is a straightforward setup. Keep in mind, right, we were not interested in point estimates. So the question was not, right, so for the, let's say, for packet 37 into the future, what is going to be the expected value of the delay forecast? The question was, what's going to be the delay distribution? And how can that be? Can that be expressed? And how precisely can that be expressed? Okay, so we then came up with as I said, with a certain tokenization approach. Now this is all here in our deliverables. We also have a couple of papers that are already published or that are on the way to be published. And we threw this then into LSTM and transformers. And as I said, the outcome was this parametric delay density for the future train of the packets that are coming. We had here a particular evaluation scenario. This relates to a test bed that we run at KTH. It's in a very interesting scientific historic site where Sweden developed nuclear fission. It's totally fine to be there now. And taking a particular latency collection tool that we had been establishing for open air interface into account, we collected trains of packet interarrival times, and then actually tested them with the course. We built then these predictors and then evaluated them. This is here a nice plot that shows you a little bit the power of then these time series and these temporal architectures in the predictions. In the top row, so to say, you see state of the art. And state of the art relates to different types of neural network architectures where you're always after a point predictor. Now on the right-hand side, in the top, you see a graph where we're looking into the latency behavior. Historically speaking, the last 100 latency values as they were coming in, and we're looking now into the next 100 latency values as they're going to be appearing. And you see the you see, right? So the orange line is then the latencies as they're going to be appearing. And you see in green, actually, the point predictor that you would derive according to state of the art. And then around this green predictor, you can also put a kind of like a distribution if you're interested in certain thresholds and likelihoods of these thresholds. Now, if you take this time series, these temporal prediction architectures to their full power, yet now on the lower row, you see what this actually can turn into. And in particular, I guess most of us, right, we know about these triangular shapes of these latency behaviors, which is all coming from a mismatch in the synchronization between the TDD framing in the 5G system on the one hand side, and when packets are actually transmitted from the corresponding source, and that leads then to these increasing and decreasing patterns, and these repetitive patterns, and these temporal prediction architectures like transformers, they can perfectly pick them up and then also develop corresponding probabilistic expressions of the delays in a much more accurate way around these repetitive patterns. And this is a very, very strong result, we think. This can be also expressed then in a more scientific way. So we see here the standardized negative log likelihood loss, which is just a measure to compare different distributions from state-of-the-art mechanisms, and this is the curve in blue and in green, versus then these multi-step predictors that we developed in orange and in red. And this is over the increasing prediction horizon on the left-hand side. And on the right-hand side, you see how much training samples you actually need. And you see you only need a few training samples, something like 5,000 or so for this whole thing to actually achieve a relatively high accuracy. So this is just a snapshot. We have much more results in that direction, which are all pointing to, and this is maybe the main issue here, that latency prediction in general, also KPI prediction, is really something that can be pulled off, and that can be also pulled off over meaningful future evolutions of the system. So in this case, 100 packets represent something like a second. So we're looking here in the future evolution of the system over the next second. Okay, and this is, we think, an interesting result to leverage in the future. If you're interested in more of this, we're going to have a demo at EUCMC in 2 weeks that is going to show these latency predictors live. Now, I would like to come to a second deep dive, and I think I'm taking a little bit too much time. Antonio, is it fine if I go until 40?
Sure, James, no problem at all.
Yeah? Okay, good. This is the beauty of having only 2 speakers when scheduling 3. So a second deep dive is now the question, what can we actually do with these latency predictors? And there is a lot that you can actually do. We would like to put this here into the context of TSN. So as most of you know, there is in 5G a standardized support for TSN, where the central idea is that we treat the 5G system, the 5G ROM, essentially, like a virtual TSN bridge. And as you know, TSN rests on the assumption that the queuing delays for the switches along a certain route, if they are carefully managed, then essentially also the end-to-end latency can be very, very accurately controlled and forecasted, not only with respect to the average, but also with respect to the jitter. So up to a point where it can very, very accurately in nanosecond ranges control the jitter to a minimum and to a maximum. Okay, so taking this conceptual idea originally of TSN, when 5G community was looking how to integrate 5G into TSN domains, the idea was born that the entire 5G RAN could be captured like a wireless TSN bridge. Now that is, first of all, one could perhaps say an obvious approach. What basically then happens with these virtual and real bridges is that they try to express their queuing delays from the ingress to the egress. So this is captured as a port-to-port delay of a bridge. And then based on these characteristics that are forwarded all to the CNC, so to the central scheduling point, corresponding very fine-grained schedules are cranked out and are then distributed to the different switches that are implementing this, and then you get this very appreciated end-to-end TSN capability. So key for this is that you can express actually these, on the one hand, the propagation delays between the bridges, but also the transmission delays within, the port-to-port delays within the bridges. Now, if you think about that, that is, of course, challenging. Because in the case of an Ethernet switch, these port-to-port delays within the switch are very, very well managed, are expressed typically in nanosecond ranges, and have therefore are very, very fine-grained in that sense, and are also absolutely deterministic. And the thing that is always so, when you look at this way, how TSN is, how 5G integrates into TSN according to 5G standardization, the thing that always puzzles you is how can I conceptually compare the internal workings of a TSN bridge with actually the behavior of a 5G RAN? So this is you need to at least, I don't know how, maybe everyone else here in the call feels this is natural. To me, this was always something, right? And admittedly, I'm coming from the wireless domain. So to me, this was always something that I needed to wrap my mind around. And right, the reason is here twofold. On the one hand side, a 5G system, a 5G RAN, expresses its delays, right? So UE to infrastructure delay, not in the range of nanoseconds, but in the range of milliseconds, right? So you have completely different magnitude of delays, and then also you have a much more stochastic behavior of the 5G system, right? Which for times can be can exhibit a particular distribution. You might also claim this to be somewhat pseudo-stationary, but then over time, right, also these distributions actually change. Okay, so the question is, right, with this type of integration, nevertheless, if this is doing anything good, when we now try to tie 5G domains into a TSN end-to-end flows. And here is now a nice comparison. First of all, on the left-hand side, we try to show what would be actually happening if you just pulled in 5G domains in the way TSN typically ties them in through scheduling algorithms, where we're just looking at the min-max bounds. And so what you would be doing is you would be saying, okay, I have a couple different flows. The flows have a certain requirement end-to-end. I break down this end-to-end requirement towards my 5G domain. And now I need to determine a certain worst case port-to-port delay. And right now, if you were given a certain histogram or behavior of your 5G system, then you would try to capture, right, the entire probability mass of these delays in a certain way. And you already start to see that this becomes very, very inefficient, because on the one hand side, right, you have potentially huge delays if you want to capture the entire probability, entire probability space of the delays. And for those times, according to these min-max schedulers, you would also have to reserve actually the entire 5G RAN only for that flow. In contrast, right, if you resolve a little bit this exclusive reservation, you could now also express a 5G system through only certain reliability levels that are not corresponding to your min-max 100% deterministic behavior, which would give you a better delay, a shorter delay window in particular to reserve. And then on the other hand, of course, 5G systems also can schedule many flows at the same time. And so this exclusive reservation of individual time windows in particular for different flows, you can also soften that. And that is the essence of a so-called wireless-friendly TSN scheduler that we developed. This is a result that was mainly achieved by the folks in Stuttgart, University of Stuttgart, and has also been now published and is in our deliverables. So bringing this forward, you see if you employ here for a particular TSN 5G simulation scenario, if you employ the wired algorithm, just according to state of the art, here on the right-hand side, you see that as we're scaling stream reliability and we're looking into the capacity of the system in terms of streams that it can support, and you see that the state-of-the-art algorithms, as we scale them here in the scenario, are very, very limited in terms of their capacity. But if you're able to capture the latency profiles of the system and predict also these latency profiles in the system, then you can actually support much, much more of these streams, and also in a relatively stable fashion as you're scaling the stream reliability. And that is the essence of these wireless-friendly TSN schedulers that we developed. And it's a major result of the project. This is another evaluation scenario where you see, in particular, how the min-max latency scales for different, again, scheduling algorithms. And you see that for the wireless-friendly TSN scheduling, we get very, very low jitter around the medium latency for the schemes that we have developed. Okay, so again, there's a demo at EUCNC in 2 weeks. We're also going to show that. So if you make it to EUCNC in 2 weeks, then be welcome at our booth, and please then dive there into the details. I'm now ready to wrap up. So 6G must support CPS at scale. Now, this is something that is a shortcoming we see in 5G. And we think this is an absolute must towards what some believe will form into the cyber-physical continuum. There are a couple essential features that are beyond URLC and edge computing, which you could say is the 5G state-of-the-art. So performance observability, data-driven KPI predictions, over-the-loop latency control, integration into deterministic end-to-end scheduling frameworks. These are here the keywords. There are many more aspects also relating to resilience, relating to security, and so on and so forth. We're not done yet. There are a couple of key results coming out of deterministic 6G, which speak towards these dependable architectures fundamentally being possible. And we think the next step is really an efficient provisioning and then also standard integration that is required. Now, 2 more words. We have here, of course, a list of our deliverables. There are more almost now daily coming out. It's actually quite a nightmare in the project. I think no one's sleeping for the moment because we have such a deliverable storm to survive. So please tune in. There's also the webpage. And last thing, Antonio, that I want to say is we will organize a dependable 6G summer school. And this is going to happen September 8th till 10th in Stockholm. We will have lectures, in-depth lectures on KPI predictions, wireless-friendly TSN scheduling, and also exoskeletons. There will be also a couple of keynotes on dependable 6G standardization and real-time wireless 6G. And you are all very welcome to register. This is all on our webpage. From our webpage, you see right away the summer school jumps up there. I have been told that if you get to the webpage, you need to actually accept the cookies. Because if you don't, then kind of like the webpage is blurred. We're very sorry for that. There are reasons why this is the case. Anyway, so just if you're interested in this, if you go to our webpage, please accept the cookies. Otherwise, it's hard to perhaps get the registration done. If you have any questions, please come back later. You're also welcome to drop me an email. Yes, and with that, Antonio, thank you for being so grateful or so gracious regarding the time.
Thank you,
and
James.
back to you.
We have one question in the chat, that is, how is TSN over 5G requiring ultra reliable low latency communications? This will be the first question that we have.
Okay. So not necessarily. Of course, if you run URLLC, you get your hands around, in particular, UE implementations of URLLC, you get a more efficient implementation. That is true, right? So what will be actually happening with the URLC implementation is that these latency distributions, right, they would now start to become more narrow in comparison to what I showed. You would still have the challenge that you would have to, of course, manage the uncertainty. So also URLC comes with the uncertainty because you do not know what exactly is going to happen over the next second or a couple of seconds in your radio environment. And that's something you would still have to manage. But the integration would get more efficient. That is true.
Thank you, James. We have another question that is rather long, so maybe you are able to read it yourself. That basically is asking to compare these parameters for TSN and DetNet. What is the impact of what you have explained?
So, okay, I see this is here, Angel, right? Okay, good. So here's the thing about DetNet and TSN, right? So DetNet is trying to recreate whatever TSN is doing on layer 2, layer 3. Now, apart from a couple of implementation challenges, right? Conceptually, it's easier, right, on layer 2 to be fine-grained in terms of your scheduling. A lot of the DetNet concepts are very similar. So we think the core challenges, right? How do you manage stochastic elements? And these stochastic elements are not only wireless links, by the way, ladies and gentlemen, right? These are also compute elements, or potentially can be compute elements. And I have not been talking so much about that today, but this you can clearly also see that also in the compute domain, you are hitting stochastic uncertainties that you might want to characterize, and that you then also have to somehow express in such a TSN or DetNet context. So from a philosophical point of view, the core question is always how do you integrate these stochastic elements in such a deterministic scheduling domain. So everything I have been saying today about TSN also carries over to DetNet. I do not see that there is a fundamental difference.
Just one comment to complement this explanation, because we have some experience in Predict6G because we implemented one of these DetNet things, okay, and check. And there are basically two ways of doing this with satisfactory results. The first one is you put a DetNet layer on top of a TSN switch, and then you use the TSN stuff for everything, okay, and the DetNet is just doing forwarding on layer 3. Or you remove completely the MAC layer of the Ethernet switch, meaning that you bypass the kernel drivers and everything, and you do it yourself at the DetNet layer. Okay. So these are the two ways of doing that works. Okay. Any solution that is in the middle will introduce completely random delays that you cannot control.
Exactly. That's what I would also suspect. Yes.
Yeah. So Jose from Siemens is also asking a long question, so you better read it. So basically, he's asking what is specifically configured following the OPC UA FX approach, and wireless friendly results about interleaving.
Okay, the first question I don't understand.
If you can hear me, I could maybe clarify, Professor. Can you hear me?
Yeah.
Jose, please go ahead.
Oh, thank you
Good.
very much for the presentation and also for letting me clarify. You mentioned in one of the slides that OPC UA FX is used to so that the application can speak to the or so that the network is friendly towards the application. But then what is specifically done there? I mean, is the application speaking OPC UA with the DETnet controller, or what is OPC UA then used for in that case? It was in one of the first slides in the first part.
Yes, so we had the ambition to pull in more of this application specifications into OPC UA FX. This was a little bit, let's say, de-emphasis during the lifetime of the project. Jose, what we can do is I can investigate there a little bit more. So I did not focus much on that today.
Okay.
And I can let you know what we.
But if there is a deliverable, I can read up all.
Exactly. Yeah, that's what I'm going to do. I have your email, I guess. So.
Yeah.
Yeah.
Thank you very much. Yeah. Great. Thank you.
Okay, and we have one last question regarding the use of PTP. If PTP is always required for time synchronization in TSN. James?
It's always dangerous to say always.
Exactly.
So in my mind, yes.
I mean, I will say depends, no? In TSN, yes, for sure, because TSN mandates PTP.
Exactly.
If you want to do something TSN-like with other technologies and so on, there are other options. I will say that. So thank you very much, James, for the talk. This was really, really interesting. Now I will pass the floor to Gergely.
Yeah.
Gergely, are you there?
Yes, I'm here.
Great. Thank you, James.
Trying to share the presentation. Okay, let's share this one. Right. So I hope you see the presentation, and I hope you will see the presentation also when I switch to presentation mode. Okay. Okay, so hi everybody. So seems that time-wise we are more relaxed, but I won't take, I hope, much more time than I was scheduled to. So let's quickly start. So the presentation is about our project, this 6G, and where I'm at the same role as James was in the previous one. So I'm the technical coordinator. I guess that's the same as technical manager, by the way. So we are kind of coming from different angles. So instead of seeing how far we can go with deterministic networks and TSN and DETnet and these type of things, we are targeting the service-oriented, service-centric, and features and network programmability to see actually how the network programmability, how far we can go with network programmability without necessarily having these like reservation schemes or more, I would say, more deterministic schemes. So, and why did we do that? Because I think for 5G, we had a lot of promises, basically. So we said that basically 5G should, besides, of course, having high performance for diverse applications, we also promised the converged infrastructure, more automation, more programmability, and because of that, simpler management. and also integrated machine intelligence. But like the color code is kind of depicting what I personally think about the promises. Of course, we delivered on the performance, but I think we were a bit less well delivered on these kind of more soft aspects like automation and integrating AI. So basically, I can tell that yeah, a few things remains for 6G, which is good because then of course we still have an XG. And these are mainly, I think we will mainly need to focus on simplicity, automation, and network programmability in 6G. And the challenge is basically, and this is again like some more generic slide from Ericsson, that basically, as also James pointed out in the previous presentation, the applications are increasingly diverse, and you know, we are ranging from these very small devices will need only a couple of packets per day towards the normal mobile broadband, which where you are mostly media centric these days, I would say, and also towards these very high demanding robots that require kind of very stable latency and etc. So we will need to support all of these without building like standalone systems for this. So I mean, we have one system and we have to use that system to support these applications. And of course, ultra high performance and low cost at the same time, because of course it seems that the budget of the operators is not increasing too much, but of course the bandwidth and the bits that they carry it does. So this is a challenging landscape, I would say, and because of that we need a platform that basically enables quick development and also easy operation and quick introduction of different services and applications. And this was basically the starting point of our project of this 6G. And I would say that we try to tackle this challenge by three main architecture novelties that we studied through the project, and we also implemented, and we'll demonstrate basically, like the preliminary demos will be seen at UCNC at our booth, at least one of them. And of course, we also plan some final demos later. So basically, the first one is this service-centric architecture that we were kind of saying that if we want to have this big range of applications supported, well supported, I would say, then we need to have a more service-centric architecture with rapid service deployment, and even based on request, on UE request. Then we have to also do a much better job in optimization of optimizing these services. So if we have multiple services and they are not, very strictly isolated, then of course we need to do a proper job with the optimization, and we introduce basically 4 different optimization loops. I will come back to those. And here we introduce some AI functionalities as well. Currently it is deployed on the 2 higher layers, but the other layers, I would say, they're also AI ready. The loops are there, so it's kind of not saying easy, but doable to include some AI functionality there. Then the third big thing is the cloud nativeness. So we were always saying that the 5G architecture is cloud native because we had the SBA, etc. But we tend to forget about the user plane, which was less cloud native, I would say, or I could dare to say that even it was not really cloud native. Now we are introducing some tricks there as well to make it, I would say, more cloud native. At least it would look like as it was cloud native, because we are employing the same principles as in the like in a Kubernetes domain, basically. And we are also applying mostly transparent hardware acceleration. I will come back to the details. And of course, we are also discussing the next steps. What's next? Is it enough? Because applications are evolving as we speak, especially with the advent of AI. We'll probably see very different traffic profiles in the future. So do we want to make the network even more like diversely supporting those use cases? We will come back to the initial ideas. That is not part of the Desire 6G project per se, but we are also thinking on a continuation and possible future work. But first, let's talk a bit about the service-centric architecture. We'll try to be a bit quicker on that. So, of course, in our case, what is the service? It's a quite heavily overloaded term anyway. So in our case, the service is what the system provides to the end user. So what the end user actually sees. And this is essentially, in our case, a packet handling or a network function graph with some quality of service, or basically KPIs or requirements that are needed for the service. And and basically that is, I would say, similar to a network slice today, but it's much more lightweight and easier to handle. And then, of course, we have to support multiple of those services, as I mentioned. So we also have to have some system-wide inter-service policies, which are there, of course, but I would say this is pretty much state of the art. And then, of course, we have to make sure that those policies are applied at different levels. And for that, we have some, I would say, quite new traffic management schemes. Then, of course, we need to support the rapid deployment, even dynamic deployment. I will come back to these steps, and I can kind of confirm that all those steps to actually deploy yet another service to a mobile network, in our case, the demos, is in the second time frame, basically. Okay, but first a bit about the architecture. I will not go to the details for the sake of time, but these pictures will be available after the webinar, so you can come back at any time. So basically, on the left, you can see the architectural blocks. We basically have like three main layers: the service management and orchestration layer. This is kind of ORAN, the ORAN specific, or well, not really specific, but the ORAN support layer for managing the services. And of course, we added this dynamicity to that as well. Then on the middle layer, you have the agents and the network function control plane. Those are kind of managing or configuring and managing one specific service. Then we have the programmable data plane layer with the IML and the underlying hardware and in the infrastructure that is kind of isolating the actual runtime functions in the system from the upper layers. This way, generating a cloud-native view. And then the service description, you can see on the right that it's basically a service graph, a directed service graph. And I also have to mention that in Desire 6G, since we have like different use cases and we have to support different types, we specified basically two types of services: edge-to-edge and end-to-end. And basically the final demos of the project will show both. So demo 1, which is drone control and optimization demo, will show the end-to-end, and the other one, the digital twin with the robotic dog, this low latency and federation-based demo will show the edge-to-edge. So the first one. Quick example, basically, let's say you want to deploy a simple, basically dual queue system, well, similar to a dish server or something like that, and you want to deploy like a low latency and the default mobile broadband service. Low latency here could mean only that you are preferring low latency for that queue. For example, if you use your mobile phone with, let's say, you have meetings like this, and you have some background traffic, you pretty much don't really want to treat them the same way, but you would kind of use your low latency service, low latency interface for your teams or whatever application that you want to run your teleconferencing on, and you would kind of use the other interface for the background traffic or for some other download traffic or whatever. And in this case, of course, you will have different network function graphs per service in the network. For example, you probably don't want to go through each and every modules with the low latency service. You probably also want to use a different path, maybe some edge breakout, whatever. It's the possibilities are there basically. And yeah, it's pretty simple to configure. And on the QoS part, you can basically have the on the UI level, you could have like dual queue, or on the network level, you also have basically like this dual queue in the system. But of course, you can do weighted fair queuing among the users on the same queue and whatnot. So there are a lot of possibilities. And we also have like a novel traffic management scheme where you can actually kind of encode the same principle and still use one queue only. So that is especially good for the hardware targets where you don't have too much queues. Okay, but this was just an example. The service creation is, I would say, pretty simple. It can be an intent-based, or in our case, it's an intent-based system. So basically, the user or the service provider comes and defines the intents first, either through SLAs or through some human language, and it will be translated basically to a network service graph and to additional parameters and stored in the service catalog. These are the details. I think I will not go into them, how the message flow looks like. And then basically we have this dynamic service deployment where you start from the logical view. And the logical view is only describing the network functions that are essential for that service logically. And then first you start with allocating the sites based on different requirements like latency requirements, cost factor, etc. And after the site allocation, you are talking to the site itself, basically to each and every site, to the local IML engine that will actually further do the deployment by either by talking to the local Vim, so maybe in our case it's Kubernetes, or by configuring the necessary functions directly in hardware, because of course we need to support hardware as well on the sites, and of course the Vim doesn't do that, so Kubernetes doesn't support Tofino switches or SmartNICs, for example. And basically it's also the local site's responsibility to take care of load balancing, also adaptation logic between the sites. So like, I don't know, set up a VXLAN tunnel between site 1 and site 2 and things like that. This is not part of the logic, the service logic. It is part of the infrastructure because it can be independent from the service logic. Okay, and the last step is the physical deployment. So basically after having all the necessary components in place, physical deployment takes place. On the x86 or on the CPUs, you can use the Kubernetes Vim. On the hardware, you are doing the deployment directly. And this way, you are kind of putting together the hardware and software world, I would say, quite seamlessly. And you can do this, different. So of course, if a network function, I mean, yeah, I didn't mention that for network functions, we are typically using the P4 language, which is a portable language. You can use it on the CPUs. You can also use it on some of the hardware units. So basically, if you have like a P4-based network function, the IML has some freedom to choose where it deploys. And because of that, it's kind of transparent what function to accelerate. And you can do these optimizations pretty much automatically. Okay, yeah, this is the deployment details, but I will not go to it. I will leave the slides here anyway so that you can check it later. Then, of course, when we have a service deployed, the user have to attach it. But this is, I would say, pretty simple. We are using Mostly we are using state-of-the-art methods to do that. And this then basically the UI will see yet another PDP context. I would say yet another interface that it can use. And in this case, in this way, it can use multiple services. All right. Yeah, I have a few slides about the cloud native functionality, which I think is quite interesting. So basically, the background of this is this network function decomposition. So we always have a kind of a control plane part for the application and the data plane part for the application. Data plane part is the actual code that processes the packets. And the control plane is the logic that talks to the external world and configures the logic in the data plane, so the tables and the classification, etc. And then we have a logic in between the two. This is the IML, basically. This is, as I said, this is basically a hardware abstraction plus an infrastructure support layer. And basically, it supports the P4 runtime logic. And I have to note that P4 runtime, although it's called P4, the first two, but it's not P4 specific, so you can actually configure other pipelines like BPF pipelines or direct DPDK pipelines if you have the proper binding. Okay, so first let's see the aggregation and the separation, how it looks like. Let's say you want to install a new network function in your system because a new service requires that. What to do? You already have the network function in the repository, the network function code basically, and the binaries, probably containers, both for control plane and the data plane logic. And of course, for the data plane logic, it's mandatory to have the P4 code because for the hardware target, it has to be dynamically aggregated with the other codes in the target. That is what is done in step 1, basically. We have to add the NFDP, the new NFDP code to the multi-tenant P4 program that is already running on the hardware or the software. But in the software, you have multiple options because you can also run these different boxes, this yellow and the orange and purple boxes as containers. You don't necessarily need to aggregate them. You might want to aggregate them though, because of performance reasons. So again, this like leaves the room for optimization also on the software part. But on the hardware, you need to do that like this, because the hardware typically, at least the Tofino switch, runs only like basically one program at a time. Then the new program will be deployed to the ASIC. Then you configure the control plane endpoint in the IML proxy, and then you kind of deploy the control plane and connect it to the like northbound interface of the IML proxy. And in this case, the control plane, as you can see on the right, these different control plane guys, the red, the yellow, the orange, and the purple, they all see the switch as if it was only their code running there. So it's really isolated in that sense. Although the hardware itself cannot do isolation, but through the IML we can do the isolation for the control plane logics. And in this case, basically we can mimic virtualization also in the hardware targets. So this is basically one step towards the cloud native like user plane. And the second step is the load optimizer logic, basically, that we have in the IML layer. So on the left side, you can see the logical view is very similar to like if you would use a Kubernetes service where basically the client is the control plane and the server is the data plane. And you don't necessarily need to know the complexity of your Kubernetes service, from the client perspective. You just send the packet to the external IP address or the node port or whatever, and then Kubernetes takes care of the underlying complexity. Selects a worker for you, etc., and then you will get the answer. And you don't know about this complexity. We wanted to do the same with the network functions, and this is why we have the actual view is on the right. That the NFCP, the control plane or the client, still see one logical instance. But under the hood of the IML, you have the load optimizer. It can do heavy hitter offload if you have like hardware instances and software instances running for the same service, because of course the hardware is more memory constrained and the software is, you know, more performance constrained. So you might want to run them both. And if that is the case, you want to kind of direct your traffic that only the heavy hitters are going to the hardware. And of course, the new flows or the lightweight users are going to the software. Besides that, you might want to do also load balancing. And if you support with your network function logic, you can support also your load balancing key to the system. And then in this internal load balancer using those keys, actually, it can do like a load balancing for your service. And this is I would say pretty automatic and pretty dynamic. Also, when you create a heavy hitter and you move your user from the software to the hardware pipeline, you want to be sure that that your table entries are arriving there first, etc., etc. So there is a bit more magic behind that, but this is the basics. Okay, and then basically third big, I would say, undertaking of the project or the architecture is to actually have these 4 different control plane loops, which work on very different timescales. So basically from the slower timescales to the upper, first is the traffic management, where, as I said, we have a quite novel scheme that is based on packet value. And it is on a per packet level, so it's way below this millisec time frame. Then we have the local optimizations. I would say it's in between the 10 to 200 millisec. It is similar to the near real-time recon run. Basically, the IML can do this load optimizer changes also in this time scale. And and we are using SDN controller as well, but that is, I would say, coming from an external project. So the yellow components here are external components. Then we have the multi-agent system on the service layer, basically. So this is a per service optimization agent or optimization engine. This works on the 100 millisec to 1 sec time scale. And then we have some possibility for global optimization, of course, because we have this entire service deployment on the second time scale pretty much, so a few seconds time scale. We can do that basically on the fly without sacrificing too much performance from the system. So if you really need to do some redeployment because you cannot really solve the problem locally or on the service level, you can do that fairly easily. Okay, so like for the layer 1 example, so this traffic management, not really layer 1, sorry, but this traffic management example is basically on the picture, and this is coming from Work Package 4, so you will find additional documents describing how it works. And this is basically solving the fair sharing and also the priorities together, and based on a value-based smart dropping. It is coming mostly from previous activities, but we are integrated it to the desired 6G architecture. The data plane self-optimization is pretty much what I already described in the cloud native data plane slide, so I think I will not go into the details now. The multi-agent system that is on the, I would say, per service layer. Basically, this is a distributed control and optimization engine. It has some domain-specific agents to actually talk to the domains themselves. So, for example, we have a run agent talking to the near real-time RIC. We have a transport agent talking to SDNC, and I think we have or we will have an infra agent also talking to the IMA. And besides that, on the top of that, we have these per service agents as well. So we have a service agent for each and every service that is active in the system. if it needs an agent at all, because sometimes for very basic services you probably don't want to do this, but for most of the services you do. And these guys are talking to the inbound network telemetry system, which can also do a per service like telemetry collection, and it's also a quite dynamic. So we are using this programmable data plane to also install different telemetry probes on request, basically. So you can do it quite dynamically, instructed by the multi-agent system. And yeah, I only have this service redeployment functionality, the details of it on the slides. I think I won't go into the details. The bottom line is that whenever the first three layers are failing to solve the problem with some of the KPIs, they can always signal to the SMO, to the top layer, that please, we need a redeployment. This is the problem with the this like latency or jitter or whatever is violated. And then we can kind of partially or fully redeploy a service. Okay, I think that was pretty much all that we have from the architecture discussions of the first 2 years in this 6G, and most of it is already implemented or under implementation as we speak. You will see, as I mentioned, you will see demos on UCNC, and we will also have final demos at the end of the project. And yeah, besides that, we were also starting to discuss what's next, because of course we can do a lot of things with a service-centric and optimized architecture, but there are some future workloads that might need even more optimization, and might give us even more insight to what they actually require. And this actually leads us to the goal-oriented or semantic communication area, which is, I think, well, it's hard to say whether it's just a new hype or it will be a big thing in the future. But at least with the advent of AI and distributed AI, this topic is coming, and more and more people are talking about that. Because of course, if the AI engine knows what they want, much better than a traditional, service like I don't know, a YouTube service or whatever, we might use that information to fine-tune the network, and we can do it on different levels, of course. And I don't even know when people talk about semantic communication or goal-oriented communication. For me, it seems to be also a bit overloaded at the moment. But we do have different levels, and since we have this architecture that I have shown you like the last half an hour, we could identify some hooks where the semantic information could be used to influence the system. Of course, probably the easiest way would be to use this in the service selection. This is very straightforward, I would say. Which service should we use? Should this, I don't know, AI engine or different service or different application use could be decided on this level. But of course, we can go much further. We can say that we can directly influence the quality of service. As I said, we have a value-based system in this 6G, like a packet value-based system. So that packet value could be directly set by the semantic agents or communicating parties. And of course, there are a lot of questions with these like how can we trust these inputs from the different agents and applications, which are, yeah, of course, we need to have some proper interfaces in place. You can also go even further. So you can even like change how on a per packet basis, change how the network function is executed. So for example, you can have this semantic chaining support that I might want to skip, for example, layer X or network function Y. But you can go even deeper, of course. You can influence the scheduler directly by the semantic inputs, like in the semantic scheduler case, or you can even do semantic coding. You can even go as far as AI agents talking in the analog, with analog waveform. Of course, this sounds crazy, but this is, this could be possible. So I think there are much more open questions than solutions, but at least we did the initial mapping, and we are quite confident that these inputs could be very well mapped to the architecture if it would look like as we proposed in the project. So yeah, this is for the future. This is nothing that we have in this RCG at the moment, but we are thinking on continuation, and this could be a possible area to study in the future and to really integrate it with the existing architecture. And of course, again, the big question is, as always, is gains versus complexity. So yeah, I think this is ultimately this is the questions for everything. So like when we are talking about programmable networks and these programmable data plane, etc., we are always dealing with the programmability, flexibility versus high performance. So we have to have a good trade-off. And that is what we aim for. Okay, but thank you. I think that was all from my side. And now open for questions.
Thank you very much, Gabriele. So we have a first question in the chat.
Yeah, okay. Let's switch to the chat then.
And
Okay.
remember, we can see your full screen, okay?
Okay, yeah.
I can read it. Hi. When you say distributed AI, do you mean general AI compute that is connected via the network, or AI models that are part of the network management operation as AI agents?
All right. Let's okay, sorry. Now I see the question. Okay. I'm referring to more general AI, so AI applications that are using the network in that sense. But of course, we are also using some distributed AI methods in the agents that are optimized in the network. So in the mass agents, they are essentially distributed AI models running there. But when I talk about this semantic cogorient communication and distributed AI, I'm more talking about layered AI models that are using the network.
Okay, thank you. While other persons in the audience provide more comments or questions, I would like to ask you something, because this is something that we have tried multiple times and still we don't know exactly how to do it. I have the feeling that managing queues with programmable devices is not something easy at the moment. So what kind of approach do you foresee for that?
Well, it's not easy, but of course, I think yeah, you can come. Yeah, you can actually view visit some of the more detailed presentations. But I think we are kind of believers of this value-based queue management because of course that gives you a certain freedom of choosing distinct priority or this fair queuing style. So you don't necessarily need to have these very, like in most of the cases, if you have a more complex use case or a more complex traffic management case, with multiple services, multiple users of these services, etc., then you typically need these hierarchical queues, which is, I agree, it is not very straightforward, and especially on hardware targets, it's very cumbersome. On CPU is also not very easy because you can lose performance. But so that's why we believe that basically with this value-based system you can kind of move the complexity a little bit to the value generation part, which can be more distributed, and then the queuing part itself could be quite simple. So you can just drop the lowest value if you have a congestion.
And Gabriel, this has been implemented already? You have
Yes, this has been
prototype
implemented
of
and tested already, yes.
Okay, in P4 or in any other language?
We have P4 implementation for also for the marking and I mean queuing is something that is a bit more tricky in P4 but that's also done, and we have DPDK implementation in software.
Okay. Okay, wonderful.
And there are multiple papers. I can send you some papers at the end of the presentation.
Wonderful. Thank you, Gergely. So is there any other question coming from the audience? Or I would like to do one final question to both our speakers, to James and Gergely. Angel Martin is saying, thank you, very interesting presentation. You are also identified situations where the four control loops decide not to complementary actions.
Yeah, that's a very tricky question because of course if we allow the control loops to have the decisions, then they might come to different decisions. I think that's the basic of the question, and I think yeah, we have to study a bit more in depth that. So far, we are thinking on this simply priorities that is always the first control that has to try to solve the problem, and if it cannot do that, then we kind of propagate the problem one level above. But I have to admit that that implementation-wise, we didn't really have this very nice solution, and there might be solutions that require more clever thinking than that.
Perfect. Thank you, Gergely. James, are you still there?
Yes.
Wonderful. Thanks a lot. One final question for the three of us, and I will give my impression as Predict 6G. Okay. So what's next? What do you think we are missing in this area of dependable, deterministic, whatever you want to call it, networks that we are missing right now and we haven't researched, and we need to look more carefully? So maybe James, you can start.
Well, I think there is a lot, right?
Yes, pick one.
Let's say it like that, right? So if you look a little bit back and if you see conceptually what 5G did, right? So 5G, basically 10, 15 years ago, invited the German industrial automation industry, right, to understand these automation applications. Automation industry told them what they were expecting from a wireless system. And what they were expecting from a wireless system was a wire. No surprise there. Yeah? Why were they expecting a wire? Because, of course, if you're an industrial automation company, you don't want to change your control algorithms. Right? Okay. Now, and this led to the rise of three things that are essentially all in the spirit of the wire. That's URLLC, that's TSN, although TSN was not originally in the 3GPP realm, right? Rising, but it was coming up at the same decade. So in a sense, right, it's coming, you can argue if it's coming from the same spiritual root, so to say, but it falls definitely within this philosophy. And also edge computing is a push exactly in this direction, right, towards the wire. Okay. Now, let me say something as professor at KTH and not the technical manager of deterministic 6G. If I look at the commercial reality, right, except for a little bit TSN, nothing is really happening. Right? We do not have URLC UEs. We do not have edge computing, at least happening at the scale what we had been envisioning 10 years ago. And I think the reason is simple. So cellular infrastructures will never be a wire. Okay, and if you're asking, Antonio, what are we missing? This is now the answer, right? I think it's futile to work in the direction of a wire. This will not fly. These systems are too big. They're exposed to too many different elements. And in a sense, so the reason why we don't have URLC is it's just too expensive for current contemporary market forces.
Well, following this line of thought, what I think you're really saying is that what we need is a use case. What we really need is an application.
No. The use cases are there, Antonio. This is not the problem. right?
Which ones?
But the use cases are they're not running at scale on the infrastructure because the infrastructure cannot provide what the use cases thought the infrastructure can provide. Right? The use cases are conceptually, right? The use cases are, this is like 20, 15, 20 and more years old, right? So at least on the CPS automation side, I think the following will happen. So we will provide, right? It doesn't fly to provide a wire, right? But what we can provide is a system that has a certain notion of what it can provide, right, within a certain, let's say, time perspective into the future. Now, the really interesting question is which applications are actually able to utilize that, which requires a certain redesign on the side of the application stakeholder. Those applications that can migrate into that world will become wireless. This is no doubt. Those applications that cannot do it, either commercially or technically, and there are such applications, they will perhaps remain wired.
And this will depend basically on the requirements in terms of jitter, most probably, on variation of the latency.
No, this is more. This is not only jitter, right? So you need to, right, the infrastructure fires you a distribution of its response time, right? So think in terms of, right, high layer, responsiveness over the entire loop. Responsiveness meaning I'm having a certain real-time input and I need an actuation output, right? And I'm just feeding that into the network and, right, or into the infrastructure and I get something out, right? So the infrastructure tells you, okay, let's say over the next 30 seconds, I can realize this distribution on this response.
But do you foresee, James, that this type of, because this requires a complex API and a complex understanding, and I don't think it never flies. Well, maybe I shouldn't say never because, of course, that's dangerous. But we did have some similar, in the past, like even in the very, very early past in RSVP and things like that, we have to reserve and then we can be deterministic, and of course that will tell us exactly how many bits per second it will want to have, but it will never does that because the poor developer doesn't know that. And I think what I miss actually from this area is simplicity, and I think there could be a lot of services between this very default mobile broadband which doesn't guarantee anything at all basically, and this very deterministic TSN URLC like world which is prohibitively expensive, as you say. I think that is true, but we don't really have anything in between. That's my problem, I think. And we could have like latency preferred service as I mentioned, for example, for this type of audio calls. Maybe it could be could utilize some latency preferred service. Of course, currently probably network is just too good. I mean, without congestion, of course, it's not much to experience. But in a more congested environment, maybe if you are walking on the street or whatever, you would try to use some of those. And this could be also a win-win. I mean, because the network doesn't require more resources to use for the same user. For the same resources, you can actually use shorter queues for those services. Shorter queues mean less resources in the system, and even with shorter queues, these type of applications would be more happy. Basically, the quality of experience would be nicer. So you can imagine that if the delay spike goes up to seconds on a Wi-Fi network without any services, then it could kill this type of communication that we are doing. It's probably good for downloads, for peer-to-peer downloads, maybe for YouTube that can buffer 10 seconds, but not for this type of communication. And I don't really see that this like in between TSN and normal best effort is addressed at all by 5G at the moment.
My main question is if we will be able to have some mechanism by which we can adapt applications to this concept of not expecting a wire. Okay, for example, one of the things that we have worked in Predict 6G is clever or smart, as you want to say it, buffering mechanisms that can adapt a little bit, okay, the application to the jitter expected in the network, because of course, since we are dealing with multiple technologies, we have the same problem of not behaving as a wire, okay? And of course, there are applications that can play with that, but there are a lot of others that can't. Simply, they will not adapt to this kind of behavior. So maybe more research also on trying to find some ways of making these really wire expecting applications to something more wireless can be done. This is something that probably is something that we can work on. Okay.
Yeah, I fully agree that this application redesign will be needed for those applications that are still requiring a wire if they want to use wireless. I think that is inevitable.
That's clear. I mean, some way of relaxing the requirements that they have is mandatory, because we are not going to be able to achieve wire performance in the wireless, not in the near future, and not at the expected price. So James, basically what I was saying before about the use case, I was meaning that it's not economically viable right now. So basically there are no use cases with commercial success that allow us to develop this technology into something that is cheap enough to reach the global market. This is what I was trying to say. Guys, this was super interesting discussion. Thank you very much. And some final word, or we close?
Antonio, there is another question in the chat.
Oh, okay, sorry. In your opinion, are TSN networks mainly suited for private deployments rather than public networks? I can give you my position as Predict 6G because we are working on global deployment. So our idea is that it will be used for a specific use case. It will not be used globally because it doesn't make sense, but we may have this kind of deployments in a public network, okay? Of course, an evolved public network, not the one that we have currently. Maybe James and Gregory, you want to say something regarding this?
This is broadly fine. I mean, there will always be a certain local confinement, whatever you want to call it, private deployment or.
Yeah.
Yeah, so it's not really private or public, but local or global. I think that's the main thing. I agree that it most likely be a more private or local deployment. So saying that, and of course also like in this factories and these more confined areas, I think that is more likely to happen.
Okay. Okay. Thank you very much for this. We will make this recording available in the different web pages of the project. Thanks a lot for joining us, and thanks a lot to our speakers.